Let me first start by thanking you all for attending our 10th data engineering meetup and our very first meetup in webcast form. It's also for me the first time I do such a thing, so please bear with me, it's a little bit unnatural. My name is Edwin de Jong, I'm your host of tonight. I'm a data engineer with Big Data Republic here in Nieuwegein, and I've been busy with data science, analytics, and all kinds of software engineering projects in the last 10 years as a professional. And as some of you know, I think most of you know, this specific meetup has been in the making for quite some time. Originally on March the 5th, which is already quite some time ago, we had invited Asterios Katsifodimos, Adel Achter, Stephan Ewen, and Viktor Klang to share their perspective with us on stateful function as a service at Kinopolis Cinema in Utrecht. Unfortunately, that meetup didn't work out. Due to the onset of the ongoing pandemic, we had to change the program last minute and had postponed the topic until now, after the holidays, of course. Despite the delay, we are very happy that 3 of the original 4 speakers are here to present to you today. These are Asterios Katsifodimos, Assistant Professor at Delft University, Stephan Ewen, CTO of Ververica, the company behind Apache Flink, and Viktor Klang, the Deputy CTO of Lightband, and Lightband is mostly known for Akka. So our program will start with Asterios introducing the stateful function as a service. So the question there is, the idea is really to have a little bit of a gentle introduction. What are the key challenges? Why would you want to have state to begin with? And which design decisions do we want to make in designing such a system? After the introduction, we have 2 different implementations that use form of stateful function as a service. Viktor Klang will present to us Lightband's take on distributed state. Their current working project is named CloudState. We will see how it connects Knative, gRPC, Akka cluster, and Graal VM on Kubernetes. Our 3rd speaker tonight is Stephan Ewen. We're very happy that Stephan is with us. Stephan will present StateFun, bridging the mature stream processing of Flink with function as a service. The idea is that you will gain new and powerful abstractions useful for distributed data processing while delegating underlying technology to cloud providers. Since stateful function as a service is quite a new topic, we believe that there will be a lot of open questions, also I guess for the implementers, but also from you. So following the 3 speakers at 8:10, hopefully we'll make that time, I will host our speakers in an open panel discussion. There, the idea is that we collect your questions. We've also prepared some questions of our own during the meetup, and the most challenging ones we want to present there and see, what kind of discussions it brings up. And perhaps, we go into an angle that we haven't even thought of before. And I personally would like to see maybe a sequel to this, see how it connects to maybe a cloud provider, for example. So please don't be shy in the comment section, just write down your questions if you have one. So finally, before I will introduce Asterios, I want to give a short thank you to everyone who helped in the preparations. Ruud-Jan Poel, who has been tirelessly bringing everyone together here and has been the main organizer. Annika Hoekman, she has provided us with all the materials to communicate the event to you. And Joris Boekela, who supported us in the preparations. And I would also like not to forget the organizers of the original cancelled meetup in March, Diederik Jan Lemkes and Axel Goblet. Yeah, apologies. And this event would not have been possible without our main sponsor, Big Data Republic. Big Data Republic is a boutique of specialist data engineers, data scientists, and cloud architects. And for the past 5 years, we have helped all kinds of organizations to be efficient and sustainable. We do this by designing, building, and integrating powerful data solutions. So I really speak for all of Big Data Republic by saying that working on new technologies and new paradigms make us all very happy. And yeah, I've done that more than enough. No, not more than enough. I could always do it more. So we just get excited by learning and understanding, while at the same time, being knowledgeable and professional. And that's how we also want to present ourselves to our customers. And yeah, we really want to make solutions that have an impact. That's why we, as Big Data Republic, are really happy to support these kind of meetups, for us to learn from them and also to share in all the excitements about new technologies. Finally, we really strive to be conscious of our impact to our environment and our society. That is really one of our core challenges, not just for Big Data Republic, but for all of us. So we strive to do that by being transparent, as transparent as possible, not just to our customers, but also to end users and of course also to you. So if you have any questions about Big Data Republic, don't hesitate to ask. Maybe at the end, there will be breakout sessions. So please don't be shy about that. So our first speaker today is Asterios Katsifodimos. Asterios is assistant professor at Delft University of Technology, working on stream processing, systems for scalable AI and ML, and data integration. Lately, his focus also entails solving the state problem in the function as a service paradigm. Asterios, thank you so much for being with us tonight. And without further ado, please introduce us into the land of stateful function as a service.
Perfect. Thank you, Edwin, and thank you for inviting me. I'll try to share my screen and see what happens. I think I cannot share my screen, but only Microsoft PowerPoint. So I'll do just that and see what happens. Can everybody see my screen?
Yes.
Excellent. So a few words before I start. So basically, after my talk, there will be Stephan and Viktor giving their basic presentations about their take on stateful functions. I'll try to give some motivation first on why we need state and what are basically the design, the ways that we can design basically scalable applications in the cloud. And then I came up with a list of some, let's say, requirements or desiderata for the stateful functions as a service systems that are going to be developed in the future. Now, the list is not complete, but we can discuss in the panel what's missing. Good. So to do that, basically, I will use an example throughout the presentation, which is, let's say, a microservice architecture and how you would do it in 2020. Let's say that we have an order service, which basically keeps track of all of the products that somebody chooses in an online shop. The payment service, which takes care that when you want to charge a client for the things that there are in the shopping cart, you can do it. And the stock service, which for every product keeps a counter. Okay, so basically to check out an order, you have to first make sure that the payment will go through. And then you have to go to the stock and make sure that the stock is there. And if both the payment service and the stock reply positively that this order can go through, only then you can actually check out and send the products to your clients. Okay, so traditionally how we do this in the cloud is we separate, let's say, business logic and state. The business logic in the order or the checkout or the payment service is basically whatever your business has to implement, let's say business rules. And the state is simply the counters that we have for every product and whether a payment has gone through or not. So very, very simply. Let's say now that you want to implement this microservice architecture, and I'm going to give you, let's say, the easiest implementation that you can have. You will have, let's say, the three services. The three services will store all of their state into a database which is hosted somewhere else. Let's assume that there's a magical cloud that basically keeps our state safe. And whenever you want to communicate from one order to the stock service or to the payment service, you simply perform REST calls. Now, this is what most people do nowadays, and it's really a canonical, let's say, architecture, the go-to architecture for everyone. The problems that this architecture has is that REST calls among the services are extremely slow. RPC calls for every state change are also extremely expensive. So you basically, every time you have to add an order or remove an order or simply update your stock, you need to go through the network to an external database somewhere in your data center, hopefully, and come back with a response. The good thing about this architecture, though, is that the state, basically the services themselves are stateless, which means that whatever happens to the machine hosting this service or this service or this service doesn't matter. You can simply let them die, you can auto-scale, you can do whatever you want without any risk of losing any data, given that you trust your database admin and that the databases are safe no matter what happens in your cluster. Now let's try to optimize a bit this architecture and see where this takes us. The first thing you can do is basically take the state and instead of leave it on an external database that you can access with RPC, you can simply take the database and collocate it with the business logic. What have you achieved with that? Basically, every access to the state has become extremely low latency. Okay? So after this is, let's say you have very low latency of accessing your state, you can hope that your services are going to be some orders of magnitude faster and you can scale better. We still have, though, these REST calls that go, let's say, in between the services. So basically, although we solved the latency problem at the database side, at the state side, we haven't solved the problem of latency in between services. So the biggest problem that we will have here, although we have reduced the latency, is that fault tolerance in this setting is going to be extremely difficult. If that order fails, and let's say your database is gone, there is no way of you retrieving that data and you have lost all of your orders. So if you're going to go this way, you have to make sure that you have the middleware and the systems and the personnel to manage these services and how they run, such that you don't lose state. Okay? So just keep in mind that fault tolerance in this setting has become extremely hard, although we have basically done things a bit faster. Now let's get rid of basically these REST calls. What can we do? We can replace all of these REST calls to a communication of the services with some event log. What have we done here? Basically, instead of having to do these TCP connections for every one call that we perform, we simply push an event inside an event log, and eventually the receiving side, let's say you send something from the order to the stock, the receiving side is going to perform the action that we asked the microservice to do. Now, the services in this case can be asynchronous and reactive, which gives us a lot of advantages. And if something goes wrong, let's say the order service, the machine that runs the order service dies, we can simply replay the event log of all of the inputs of the order and simply rebuild all of our state. So as soon as the event log is persisted and safe, we basically can forget about keeping the state safe in this side. So this, let's say, take on this architecture has become low latency because access to the local state is fast. It has become asynchronous, which means less TCP connections because we have an event log in between the services. And suddenly, I do not have to care much about the state inside the service. Okay? Okay. Now, let's see basically how you would build this in the cloud. Before the cloud, basically, we have machines in local premises, and then AWS came up and said, I will sell you virtual machines. I don't care how many you ask me, but I'm going to provide them to you. You simply have to rent them by the hour and pay me for that hour. Okay? This worked well, and it was very easy to basically go from on-prem to the cloud, and everybody was happy. But then with time, the needs of the clients of cloud providers basically have changed. I logged in today in basically the AWS console, only to find out that there's probably hundreds of services offered by Amazon at this moment. So basically we went from the cloud providers giving you a simple VM to do your job, to basically hundreds of services that you have to choose. You have to navigate all of the trade-offs and the price and the performance trade-offs, and choose what you need to do a certain job. Now, this became quite complicated. So basically, this choice has become extremely difficult. And then cloud providers started thinking about how we can hide away all of this, let's say, complexity for building services. And what they came up with is what they called functions as a service. So they said, let's forget about all of these tools that I basically offer to you. The entry point to any, let's say, services that I will sell you is going to be functions. So you will write your function in any language you want. This function has to be stateless, which means I force you to not store anything in there. And whenever you want your function to communicate anything to the outside world, you will have to go through a cloud database or some storage or any other form of basically inter-process communication. So this promise basically of functions as a service is that as soon as you keep your state out of the function and you write your function and you hand it over to me, I will manage auto-scaling this function, which means if you call suddenly 1,000,000 times the same function, I guarantee to you that within some seconds, I'm going to fire up some functions and they're going to start running. The programming model has changed. Instead of renting machines and then doing exactly what we were doing before with Flask and Spring and all of these frameworks, you simply give me a bunch of functions, given that basically there is no state. The problem with this approach is that people love to put state inside their programs because that makes programmers happier. People would love to have function-to-function calls, which means if I have the order service in one function and I have the, I don't know, payment service in another function, I would like to be able to call payments from the order checkout. And finally, there is no transaction or orchestrations. Basically, you have to use separate programming models and abstractions to do the orchestration of functions. Okay, so the state of the cloud at the moment, let's say with respect to functions as a service, is that they avoid the biggest problems, being basically state, function-to-function calls, and transactions. And that seems normal, let's say, and it's a very good start, but we need to live there. So I'll just give you a very quick example of what happens basically in the classroom in TU Delft. Long story short, I teach the web scale data management class in the master. And every year, the students have to implement what I just showed you, stock, payment, and order service, using any of the technologies that I show you here. For example, you can use Flask, backed by CockroachDB, running on Kubernetes in any cloud that you would like to run. Okay, so the challenge, after basically we teach scalable data management to students, the challenge is for them to give us the maximum consistent number of checkouts per second, using as many resources as they want in the cloud. So basically, you tell the students, you work in teams of 5, you implement whatever you're going to implement, and you just give us an endpoint to basically attack the checkout endpoint, and our driver, our client, is going to hammer your service, and we will have a winner every year. So I've had this class running for the last 3 years, and we had roughly 40 teams, okay, of 5 persons, more or less, whom we gave around a month and a half to develop these 3 very simplistic services. We are talking about, what, 10 endpoints or so. Okay, so I would like basically to ask whoever is online at the moment to simply post inside the chat how many of these teams they think managed to get more than 10,000 order checkouts per second and didn't mess with the data. So I'll give you around 30 seconds basically to do that. Then we can review what happened. Okay, I see a lot of optimism and a lot of pessimism as well here. So somebody believes that we had 40 people. A lot of people report very low numbers. Okay, so I'll just break the news to you. Victor, that's not a valid integer.
Ouch.
Okay, so basically, I'll crack the news to you. It was none. So basically, from 40 teams, knowing about how everything works, nobody managed to basically to give us more than 10K transactions per second and do this in a consistent way. And then I was wondering myself, actually, so what's wrong with this class? Should we just stop doing this exercise? It's kind of an impossible exercise. Maybe I'm not doing a good job explaining the concepts to the students, or I've had all of these doubts. But in the end, I realized that state management is simply hard, okay? And if you think about function as a service offerings that we see right now in the cloud, avoiding the state problem is a very natural thing, okay? So the current technology basically is extremely primitive with respect to managing state in services in a scalable manner. And of course, this is touching a lot of distributed systems and database problems that have been out there for decades. For example, how to make stateful computations fault tolerant, how we can guarantee message delivery, how we can query the global state of a system at any given point, and what abstractions we should use. But what I want to say at this point is that at this moment, if we want to do anything with state that scales, we are not going to be able to do it. And long story short, we live in the stone age of cloud applications. And I like to basically give the example to the students at least, that right now, with respect to how we program the cloud, we are at the point that people were writing assembly because there were no compilers around. Okay, we have to know all the small details of all possible systems that we have in order to simply write a set of 3 microservices. Okay, now, how do we fix this? I try to bring 6 desiderata for stateful functions as a service abstractions. So the goal here is to add state back to functions as a service and offer that in a scalable manner. And I have basically 6 requirements. The first one is that even if we manage to write stateful functions at some point, that should be in a very high level language, and it should be the job of the compiler to simply take those functions and compile them down to specific implementations of systems that are running right now in the cloud. So remember the list of Amazon services, that should not be visible to the users, but it should be, for example, configurable. Just to give you an example, if you want to, for example, exchange messages among 2 services, you can either do REST calls, or you can insert a queue in between, or you can simply run, I don't know, RPC as we know it, or even have actors exchange the messages. But that does not have to be visible to the end user if we want to democratize basically stateful functions. The second requirement is that there should be a way to debug such functions, which means if you go in the cloud, something went wrong last night, I should be able in some way to replay in a local debugging environment whatever happened last night and do that with a very easy way. Okay? Now, the third requirement would be that I should have a way, for example, in the example of my microservices that I showed you, there should be a way to join orders with the payments and the products that they contain, which means there is in my cluster scattered small pieces of sharded state that I would like at some point to query. For example, to give the tax office report in the end of the year. The fourth desiderata would be that we can have holistic optimizations of service compositions. So after you have a global view of who talks to whom and in what way and what state they hold, you should be able to do a lot of reasoning and optimize, let's say, these service compositions. We still need to find ways of having version deployments and schemas and states, and to be able to transition between services of service compositions very easily. And finally, but for me, the most important is to enable at the programming abstraction level transactions in some form of service orchestration, which means if I want, for example, the atomicity of the example I showed you earlier, unless I have the payment done and the stock available, I will not check out this order. This should be provided to users in some form of abstraction. Now, I'm not saying that all of these transactions should be ACID transactions, as we have in, for example, relational databases, but we should provide some privileges in some way to those. Okay, so I'll finish now with the desiderata, and since I have only 1 minute left, just a few words about some folks that are working with me. So we are looking at the problem of stateful functions, and we are trying to basically follow the agenda that I told you one slide earlier. We do that with Marios and Pedro. I think I saw them somewhere in participants lists. And Adil, who is working for ING and is going to start his PhD very soon with TU Delft. If there's anything that you're interested to read, please go to these two references. I'll publish the slides a bit later. So what we have been working at basically at the moment is a very prototypical programming model for authoring cloud applications. So the only thing I want to say, and then I will just stop because we're running out of time, is that the programs that you should be running in a, let's say, in a cloud, in a scalable fashion, should not differ too much from programs that you write to be executed on your local machine. In this case, basically, if you declare your function state, if you have some primitives, like here we have transaction to orchestrate transactions, if you have a way to perform function calls on other functions that you have in your system, all of these things can simply be statically analyzed and compiled down to, for example, streaming data flows. Okay? If anybody is interested on these ones, please get in contact with me so that we don't have to go further. So, just to finish with my part, simply building cloud applications nowadays is like programming assembly. We need to fix this. And a bunch of ways to fix this is basically to simply demand for stateful services from cloud providers, to really support initiatives like CloudState or Flink's stateful functions, basically the two presentations that we have here. There's a very interesting project from Microsoft called Orleans that goes very close in heart to basically what we have in mind. And Berkeley is also building a system called Cloudburst on top of a key value store they are building. But in any case, if you have any questions or you want to take part in this, whatever happens right now, simply talk to me and I'll get you started. So thanks.
Thank you very much, Asterios. And if you have right now questions, this is the best time to write them down, of course, because they are now on top of your mind. What I thought was very interesting was the relationship between what you're working on, what your students are doing, and the fact that many of those technologies are actually also on our program right now. So I think it's very nice to see that it remains very, very challenging to make distributed systems. I mean, maybe it's not so nice, but it means that we are at the right apex currently, trying to tackle that problem. Yeah. So yeah. So I would like to go to our next guest. Thank you very much, Asterios. Stephan Ewen. Stephan Ewen is the CTO of Faverica, the company behind Apache Flink, of course. They are currently working on StateFun, and the idea is there to bring together benefits of stream processing with Apache Flink and function as a service in order to provide really good, powerful abstractions and really make the next generation of event-driven architectures. I've seen slides. I think they're really, really interesting. So I was looking forward to it. I still do, by the way. Stephan, we think it's great that you are willing to share Faverica's perspective and implementation to us. Stephan Ewen.
Yeah, Thanks a lot. Just a quick question. I thought on the agenda, actually, Viktor was first, and then it was me. So, I mean, I'm okay. I would be okay to go now. I just don't want to, steal Viktor's spot here.
No, that's fine. That's fine. Go ahead.
You sure?
Yeah, sure. If you're ready, go.
Okay. Then maybe give me 30 seconds to get ready. Okay.
Sorry, so much. I had the BIOS in a different order as the program itself, and that's why I introduced you first. Can you still hear me?
Yeah, no worries. Okay, I can actually go now. Yeah, I should have everything ready. Let me quickly share my screen here. Okay. All right. Does that work? Screen sharing? Let me know if it doesn't, please. Okay, so yeah. In some sense, I think Asterios has given the perfect introduction to this problem. Like, yeah, building stateful applications is really hard, and I took a quick screenshot of one of his last slides where he has this 6 desiderata and put it in the end of the application. So maybe we can actually spontaneously think how much of this can actually be achieved with a framework like stateful functions. So yeah, the idea of the whole project is like you said before, trying to see if some of the ideas from the stream processing space can actually help in this stateful application space. Because if the new generation of stream processors, and particularly Flink, have been about one thing, then it has been about state. So most of the work that has been done in there in the last years was to make large stateful consistent applications work. And there's slightly different requirements that are on the Flink side. It's primarily this real-time, near real-time data processing framework. So it's really more tailored initially to data flows. But there's a lot that it can also bring to the table of applications, and this is what we're trying to do in the stateful function project, which is a sub project of Apache Flink. Maybe a different way to put this motivation. I did find this just recently in a thread leading up to KubeCon, and I actually liked it. I liked it a lot because it's a different take. It's kind of saying also, I think, what Asterios said, but maybe from the perspective of of somebody in the infrastructure space. And it says, yeah, that we've done so much. We've done actually so much as a tech community to improve this infrastructure. Particularly, Kubernetes has evolved into an extremely powerful tool, but we're kind of missing this application layer. So we're really good at deploying stuff, but deploying stuff is only deploying and orchestrating the distributed processes is only half of what we really need to do. That alone doesn't really make an application easy to build and to use. And another way to maybe put this in my own words is if we put a non-scalable application with a database on some fancy infrastructure, we still don't get really a scalable application out of the box, right? It's not all about fancy deployment tools, but what we're kind of after is something like ideally a distributed application framework or library, and I think there's a fair chance that it's going to build on top of an infrastructure layer like Kubernetes. That if we make use of this for our application and state management, and I think it has to go tightly together. That's why the box stretches across both of those. We'll get magically scalable applications. Magically scalable is, of course, a bit of an overstatement here, right? That nothing is magic and not everything is always scalable, but it will make our work a lot simpler. And so we're talking about scalability here, but I think as Asterios also outlined, consistency is also a very big deal. Scalable computation, scalable state, and consistency are in fact the parts that we focus on in stateful functions first. But there's also a lot of other aspects, I think, that we really want to look into, like security and observability, and I think yeah, frameworks like CloudState and stateful functions can actually help with all of these aspects. Even though, like initially, and especially in this talk, I'm focusing only on the first three parts. And so one thesis that has kind of driven a lot of the work here, and if you wish, also a lot of the work in stream processing in Flink in the first place, is that this classical request response model from traditional databases is tricky. It's not the best match for what we're trying to do here. And you can see if you follow the work in, for example, in Flink or the other part that we've been doing, or let's say the stream processing space in general, you can kind of see this thesis being in there, all the time. Stream processing started, yeah, probably by now 10 years ago or so, maybe even longer. When, for example, Apache Storm was a big project. It started with something like, you know, stateless event stream processors that actually used a remote database or remote state store for the processing, and it came with all kinds of trouble. And one of the really big things that the stateful stream processing generation, like Flink and Kafka streams and so on, did was rethinking this model and not going with status in the database first. And I think that was a big success story. And my thesis is that we'll actually need something like a similar step here in the application space. And one thing that kind of is a really good pointer for a solution here is this. Yeah, I think by now it's almost, I can almost call it an old paper. I think it's from 2005. So yeah, 15 years old this year. This paper by Pat Helland, some of you may have come across it. It's kind of gotten, it's kind of become a bit famous, this life beyond distributed transactions. And yeah, the idea is really, you know, he goes all about, you know, why transactions make things hard and not scalable, and yeah, and are just a tricky primitive for certain things. And then he advocates for a different type of abstraction, which yeah, maybe I can sum it up as just stateful event-driven entities or actors. So he isn't actually, I think, calling it exactly like that, but the way he's describing it, that's how I understand it. He's basically advocating this kind of thing as a building block for applications. And I think this has a lot of yeah, I would say still promise and wisdom to it even today. And it's in some sense exactly what stream processing does, and to some extent also what stateful functions does. So maybe let's actually introduce stateful functions. So I'm not talking like super vaguely here what this is all about. Like what is the idea of stateful functions? What is the take that it has on this on the stateful serverless space, and how can we actually build something like stateful event-driven actors and still kind of, you know, stay a little true to some of the ideas of the serverless space at least. So stateful function has two aspects to it. It has basically an API to it. That's, you know, an API to build distributed stateful applications, and then it has an architecture to it that kind of maps this to like a, you know, cloud native serverless way of running this. And the API to run a stateful functions application is centered around, you know, as the name says, stateful functions. So the idea is that, yeah, you model the applications as functions, but very, very importantly, not thinking of functions as you know, as a service. One function is one service. So there's like you a service for, let's say, the user shopping cart, or a service for the inventory, but you actually have a very fine-grained way of modeling this. There's one stateful function per user, one stateful function per inventory item. Very, very fine-grained way of modeling this. And yeah, then these functions, they own their state, and they react to messages very much like, they react to messages like actors, and they communicate to each other with each other through messages. And an important thing here is by being, if you want to actually model it in this very fine-grained manner, each inventory item has its own function, then we need to have it in such a way that if a function is not invoked, it doesn't consume any resources. Similar as a row in the database that's not frequently accessed is at some point not in the cache anymore, but it's somewhere, somewhere on the disk where it's cheap. The important and in some sense, defining thing about stateful function is really this consistent stateful nature. So each function has local state. You can almost think of it as, when you work with it as if it is your local variable. So by the time you access it, there's no delay or so you have to worry about. You don't have to worry about the fact that this access might not actually go through or so. And you can send messages to other functions, and it gives you a model as if you have exactly one semantics. So a message that you send is going to arrive, and it's going to arrive once. There's a lot of, I think, there's a lot of argument how should you call it exactly once, effectively once. The important thing is that if you follow actually this model of sending messages and in the functions really working with messages and state, then at least every message is reflected only once in the update to the state. And I think this is really the key, what you need for consistency. So I think it's been called effectively once in some ways, but yeah, the important thing is it's like a transaction. If the state gets updated, then the message will not get resent. And the communication with the outside world is also strictly message driven. So each of these functions reacts initially to messages that come through an event ingress, and if they want to effect changes to the outside world, they would actually send messages through an event egress. And that's also really important, because having these well-defined channels for interaction with the outside world, you can make sure that communication with other services is also basically transactionally correct. You really don't need to worry about anything. Now there's a bit of a, compared to, let's say, classical microservice database based setups, there's a bit of a different approach that this framework here takes for persistence, and that is not actually storing the data in a database, but actually persisting it through snapshots to mass storage. Mass storage being something like S3, Google Cloud Storage, or HDFS. That's actually a mechanism that's offered by Apache Flink, which is the underlying runtime for this. And I think it's a very interesting architectural choice, because it basically it gives you a very cloud native feeling, if you wish, right? You don't actually need something like a database with persisted volumes or so for durability. The only thing you need for durability is something that's very cheap and managed like S3. And the architecture, if you look at the whole thing, is maybe best described in this picture. There's a Flink cluster which here takes care of the state managing. It accepts the initial events from the ingress. It sends the events through the egress. And then the actual functions, function implementations, like your user function, your inventory function, your shopping cart function, basically the implementation of the business logic that runs behind separate services. It can run behind a Kubernetes service. It can run as an AWS Lambda function behind the API gateway, or in a custom microservice endpoint. And all the statement messaging is in the Apache Flink layer. And when when the functions get involved, actually, then their state is supplied through the invocation directly, together with the message to which they have to react. So state and message is passed to these functions through whatever invocation mechanism you're using, and that gives the functions a very interesting property, because you can treat them as if they were completely stateless. So that's, for example, why you can put them very easily on something like AWS Lambda. Everything they need, they always get through the invocation, and every mutation they want to do, they put in the response, and then the Apache Flink system will actually apply it. So in some sense, what this thing does is it kind of flips the whole role between application and database a little bit. So if we look at a more traditional architecture, like the microservice architecture Asterios outlined initially, we have the input events going to the business logic. The business logic talks to the database through whatever the protocol is. It talks to the database, and then it produces output events. And the application logic, really, that layer has to make sure that things kind of fit together. Do I pick up an input event from the message queue, or do I accept an RPC request? Do I make the change to the database? Do I send an event to the outgoing service? What do I do if one of these things is wrong? How do I reason about retrying this, rolling this back? So there's a lot, really, the application layer has to do. Even with the best frameworks, it's not trivial. And the stateful functions approach kind of turns this a bit around. So the events that go in, the ingress events, like the requests that should invoke the functions, they don't actually reach the functions directly. They first reach the database, if you wish. So events first go into the database, where they go together with the state, and then they invoke the functions together. So in some sense, the driving party, which is the one that receives the message and then says, okay, now that I got a message, I have to do something with it. While it's classically the application, in this case here, it's actually the stateful function cluster accepting the message and then deciding what to do with it and invoking the business logic. And in some sense, the database is originally the one that reacts to put get requests from the application logic or SQL queries in a more general sense. In the case of stateful functions, actually the application logic is the one that reacts to the messages, and there's a lot of interesting properties about that. And one of the most important ones is that by having messaging and state in the same layer, we can actually do a lot of transactional guarantees out of the box, if you wish. And the application logic, by reacting, is basically, it becomes almost stateless, pure functional logic, which is very easy to handle. Let's make this a bit more concrete with an example. So let's take this very simple example of a shopping cart inventory service. We have a user called Kim that says, I want to put some socks in my shopping cart, and there's let's say the web application puts the event for this action in our ingress, and it addresses that to a specific thing, namely type cart entity Kim. And the type of the message that it sends is this add to cart with a payload of socks and 3. And the system, so StateFun will pick it up from the ingress. Let's assume the ingress is something like Kafka or Kinesis. So it will basically subscribe to that, and it will route the event to the partition that owns the entity cart Kim. Let's say this is partition A. And then it will look up the state for cart Kim. One thing that it does is it will actually check if there's another invocation for cart Kim happening at the moment, and if yes, it will basically enqueue this. So it's a bit like actor processing. There's one call at any point in time that's possible, and if this one's busy, then it basically gets enqueued in the mailbox. And if it's not busy, then it actually takes the latest state for cart Kim and that event, and it invokes it. And the invocation is, in the simplest case, just an HTTP request that goes either through a load balancing service or through an API gateway and hits the function, which is either a custom HTTP handler, or if you use one of the StateFun SDKs, then it's a simple function, and let's say the HTTP request plumbing around that is taken care for you by the SDK. So the function is really like a stateful, it's really like a stateless idempotent function. It depends only on the arguments that it gets. the current state, and the message. So the message is add the socks to the cart, and the state is the current cart is empty. So that logic in the simplest case would just say, yeah, okay, sure, I add this to my current cart. So here's an updated cart, and also I want to, send out another message. And let's say the message is something like, I want to notify the inventory service or the inventory function, specifically the entity socks, to reserve 3 items. And then it sends both back, the resulting state and the messages it wants to send. And this again, is the answer to the request received by the StateFun cluster, and then this will update the state and send the message to the partition that owns the inventory socks entity. And this is basically, let me say, pretty much transactionally integrated on the Flink side. It's not really transactions. It's actually distributed snapshots how Flink handles it. But the effect is that it's transactionally correct. Either the message gets sent to partition B and the state gets updated, or none of these things happen. It goes actually even further. Like either the message that is picked up by the add the socks to the cart message at the beginning is also either properly enqueued for service invocation, or it's left in the ingress. So all of these steps are basically like transactional. So you don't have to worry about any message getting lost or getting duplicated at any point in time. And then, yeah, the same thing happens actually on the other partition for the inventory service. Reserving 3 socks because they're currently in someone's shopping cart. So yeah, I hope that makes it a little clear what really the difference is between, let's say, the classical database approach where the business logic first gets the event and then it mutates the database, or the variant where actually the equivalent to the database here Flink gets the event and then invokes the logic. And
2 more minutes.
Right. And you may have seen it before on this slide. Like that's why, for lack of a better name, because we don't know what to call it, we call it actually an event-driven database. This whole idea of letting the database take the event. All right. Maybe just quickly, if you want to put it all together, then this is what a typical deployment would look like. Use Kafka for ingress or egresses. I think event-driven is really an absolute essential building block for something like this. You would use Apache Flink as the equivalent of the database. You would use some NFS or S3 or HDFS for persistence, and you would implement your functions, let's say in Python behind the service. And it also maps pretty naturally to a serverless stack on a cloud provider. Probably have to quickly skip over this demo. Just for sake of time, let me just quickly describe the scenario, because I think that just shows what is a really easy win here. So the idea here of this example application is a billing application. Assume you're subscribed to something like, I don't know, Office 365, and every month it actually bills you for your monthly subscription. And let's assume we're actually subscribed through something like change data capture to the database, and then we have stateful functions to manage the billing. So we'd actually have one function per user, per subscribed user, with some state like the ID, subscription status, billing interval. This function, of course, isn't always active because we're not always billing constantly, but we can actually schedule ourselves messages. That's it's one of the features of stateful functions. So we can say, function, please become active again at the next point in time when we want to do some billing. And then when this comes, this can actually it can spawn a new function with, let's say, that handles this one payment transaction, let's say with a generated transaction ID as the defining entity. And this one is then responsible to send an output message to an egress that goes to the credit card processing, charges it. It will receive the response. If it is a failure, it might retry for a few times. If it fails after 3 retries, it will remember this for let's say for the billing of the next month and so on. And what's really an easy win here is the fact, for example, that we definitely do not want to send two charges to the credit card, right? So we do want to make sure that when we talk with the processor, we absolutely, you know, do not have any duplicate messages going in and out. And the nice thing is we don't have to worry about anything here because everything is transactionally integrated. There's really no actual transactional code that we have to write in the first place. So I'm going to share the presentation afterwards, so you can probably take a look at the code here with a bit more time. But I think the interesting part here is there's no real try, no failure handling logic, no transaction logic. The only thing you really do see is, if you wish, logic for sending messages, you know, scheduling a message for later, and a little bit of protobuf logic, you know, like wrapping and unwrapping protobuf types, because that's what basically all messages are internally in StateFun. Yeah, I think that is it. Let me actually skip over the Flink slides. These were really meant for yeah, if I had a little more time. Yeah, in a nutshell, that's pretty much it. Stateful functions brings, I think, these two things here: this programming abstraction based on stateful entities, just messaging state ingresses and egresses, and then a way to actually run this on a distributed architecture with this idea of, yeah, letting state and messaging be one integrated unit and pulling the application logic out to another unit. And then that gives you, you know, all the advantages of disaggregation, independent scalability, and so on. But because we do the messaging as part of the stateful layer and not as part of the application layer, we can actually give a lot of consistency out of the box. I think I'm going to take a look at this during the panel discussion later or so. And yeah, this is a few acknowledgements to other team members. That's pretty much my talk. Thank you very much.
Well, thank you very much, Stephen. I thought, yeah, 20 minutes is very quick. Of course, it's especially if you go into technical detail, and yeah. I think it's a beautiful design, and it's also a really nice abstraction because you get a lot of guarantees out of the box without having to think about it too much. I would really wonder how this would look like if you have a much larger architecture. Am I right that the system has also been scaled up to like billions of messages or millions of messages per second?
Yeah. So I think there's some properties to this, definitely, some trade-offs that it makes. So you can actually scale Flink up to a very large size. However, all this consistency out of the box, it does come at a certain, you know, it basically represents a trade-off, right? You know, there's always the trade-off of consistency versus availability. There's many nuances to these trade-offs, but ultimately this trade-off exists, and stateful function always makes the trade-off, at least at the moment, for consistency, right? So the price for that is that two functions that communicate, if you're not sure whether a message arrived between them or not, they have to like jointly roll back and redo it, so that, you know, that there's always consistency between them, right? You can get a little more availability by just saying we decouple this and we actually let the user themselves reason about this. So there's this trade-off that it definitely makes. So if you for example scale it up, you'll eventually hit the point that yeah, so different nodes will trigger rollback in each other, and I think that's fine for a lot of scenarios, you know, like near real-time scenarios like the payment processing that we just said. I think for that it's super applicable. If you completely want to replace an online application like you know, really a user-facing web service or so, where you must have a response within a second, otherwise, you know, it's a sluggish user experience, then I think we still need to do a bit of work to actually get it there, because the high consistency comes at the trade-off that, you know, you have to at some point do certain rollbacks now and then that affect users, even though their particular state might have not been affected, but something in the larger unit was affected. So to be safe on the consistency side, you have to like jointly rewind and retry them.
Right.
So I think that's definitely worth mentioning. I think we can get a lot further than we are at the moment with this trade-off. But I think it's something to keep in mind here. So at this point, I think it's a really great match for like these near real-time asynchronous processing scenarios, like this spelling application.
Thanks.
Yeah.
So we are a little bit running late with the schedule, but that's not that big a problem. It probably means that the discussion will be a bit shorter. Our third speaker today, I already announced him, is Viktor Klang. Viktor is Deputy CTO at Lightband. I think most people know Lightband from Akka. Personally, I worked a lot with Akka and Akka Streams and Akka Cluster. So I'm really looking forward to this presentation as well. Currently, Viktor is working together with others on CloudState, which is using Knative, gRPC, Akka Cluster, and GraalVM to run it all on Kubernetes. So the idea is that applications not only scale efficiently, but also to manage, of course, the distributed state reliably and resilient. So and at the same time maintaining a global or local level of data consistency. So we get all kinds of new addressable use cases. Viktor, thank you very much for being with us tonight, and we look forward to your talk. Viktor Klang, people.
Thank you, Edwin. Let me share my screen here. It seems like it doesn't want to share it. There we go. Can everybody see my things?
I can see your screen.
Yeah. Perfect. Awesome. So this talk is about CloudState.io, and you will probably see some similarities with StateFun, but you will also see where some other trade-offs have been made. So I think this will be some interesting conversation material for the panel later. Let me see if I can actually change the, oh, there we go. So what is CloudState? Let me just go through the sort of the higher level architecture and reasoning behind why we're doing what we're doing. So in a nutshell, it's distributed state managing serverless. And those are all very vague words. And to me, or at least to us, serverless is about how you consume something or how it's perceived, rather than sort of just narrowing it down to function as a service. And one of the more interesting aspects is not having to care about the underlying infrastructure. So CloudState is a specification, an open source specification, and a set of gRPC protocols that make that specification possible. And we also have a technology compatibility kit to help validate the implementations and support for the different languages that we support. So it's both possible to create an implementation of the actual proxy, which we will discover later, but also implement support for practically any language that supports gRPC server. And of course, there's a reference implementation of the proxy based on Akka cluster and Akka cluster sharding and all of the cool stuff that we've been working on in the past decade. And we also have support for languages like Go or Python or JavaScript or Java. And technically, you could implement your own language support if you wanted to have like COBOL support or Fortran or whatever you want. So what we're trying to achieve is having developer productivity at scale. I think over the past at least 10 years, there's been this perceived trade-off between when you start something or start a development project, you either choose between being productive as a developer, or you go for creating something which can actually handle load and grow with the demand of the system. And our theory is that there is no such inherent trade-off. So what we're trying to do with CloudState is to allow developers to be productive and have fun and get their work done while being able to deliver a solution that will handle a very varying amount of load. So in order to do this, we actually needed to set some sort of guiding principles for what we do. And one of the most important ones that we set early was that we wanted to have something which is contract first, so that we know when we expose services, there is an external interface that is sort of the contract between the implementation and the consumers of that interface. And practically, when you have a distributed system and you have multiple parts or multiple components of that system being upgraded at different paces, you definitely want to make sure that when I update my part, I'm not breaking any assumptions that my consumers have. Also, it's very nice if that contract also has some documentation in it so that it's human readable and you can have a look at the contract and be able to understand what actually is provided by that service. What's also nice is if we have a contract for the service or the serverless function, then we can also derive clients how to communicate with that service. So that is very nice, because otherwise you're, at least in my experience, you tend to have to drop down and sort of handcraft HTTP requests and format URLs, etc. And it would be nice if you were just to be able to generate a client that talks correctly to the backend service. What's also nice about this contract is that you can isolate the actual implementation from the consumer, so that I can implement my thing in JavaScript or Go or whatever language, and my consumer can also have whatever language, and it doesn't matter to either. So it becomes sort of intermediate, the contract between the consumer and the producer. We also thought that it would be nice, because there are multiple ways of defining what state is or how to represent your state. And it would be nice to be able to reason about that so that it doesn't become implicit. So for instance, if you have different domains, then you might want to represent them differently. So like for an account or financial processing, you might want to have event sourcing as your way of representing that state, because it is inherently different events that suddenly, or when you sum the events, you get the aggregate, the current value of the account, for instance. But other types of state, let's say that you had these sort of view counters that were very popular on the web in the 90s, where like, this is the number of viewers that I've had on my website. That representation might be represented, or that state might be much better represented by some other form of data type. And I'm going to go into that later. The thing is that if you have first-class representations for this, then the runtime, knowing how your state is represented, can optimize how the IO and the updates and the storage is done for that specific state model. So for instance, if you have something that is event sourced, you might have a database that is optimized for just doing that work, where you optimize the appends to the event log and you optimize the storage of the snapshots and the invalidation of snapshots and stuff like that. But if you have a key value representation, you might want to go with some other database that is much better at doing those kinds of operations. So if the runtime understands how you represent your state, it can do so much more for you. And also, we sort of realize, or we have to acknowledge, that different programming language have very different idioms and APIs and how you write your code and how you format your code and everything like this. And if you have these sort of first-class representations between sort of the user's function and the runtime, then you can provide essentially any kind of API that is suitable for that platform on top of it, so that you work with it in a very natural way for your programming language. Another really important principle that we adopted is something we call lingua optima and franca. Essentially, if you only have one way of communicating, it's either the greatest common denominator or the lowest common denominator, or somewhere in there. And typically, there are things that fall outside of that need a different approach. And what we decided was that we wanted to have a sort of a two-pronged approach to how you communicate with your services. So the Optima side of things is supposed to be the fastest and the most compact and efficient way. And for that, we decided to go with gRPC, which is essentially HTTP 2 plus protobufs. And for the Franca language, which is something that as many clients or consumers as possible can speak, that is, we chose HTTP plus JSON for that. So since we have both, if you can speak the most optimal protocol, then you do that. Or if you only have sort of the most widely available thing like HTTP, then you can speak that. So this goes to what I said initially in this presentation. I think there is no inherent trade-off between those two things. So we can use any language, any programming language which can run a gRPC server. There is an infinite possible kinds of API per programming language. You could have, you could create your own, like on top of the Java support, you want to have your own sort of corporate dialect of Java or your own APIs for something specific. Or if you're using the JavaScript support, you might want to have something which is more geared toward the current JavaScript library that you're using. So you can create your own and evolve your own dialects on top of each of the language supports. And CloudState has the sidecar or the proxy, which is injected as a sidecar. And we actually compile that from JVM code, or Ake is written in the programming language Scala, for instance. We compile that via GraalVM native image into a native binary so that it can spin up super fast, which is really important when you're a sidecar process to a user's function. I'm going to display the design shortly. We also use what we already have. We have a decade's worth of really scalable and resilient distributed system software in Akka cluster. So we're really leveraging that for CloudState. And of course, we also realize that things do not exist in a vacuum. You need to have a way of interacting and integrating with the environment. So we are deploying CloudState in Kubernetes using an operator. So it's a very sort of Kubernetes native way of deploying your applications. We also decided to use these sort of industry standards, such as HTTP and gRPC, so that to the outside world, your CloudState services look like any HTTP-based service or any gRPC-based service. And having this sort of polyglot support allows for endless customization of the API, so that whatever flavor you're used to, you can get that when you program. So let's go through the architecture and the design of CloudState so you get a better sense of how we ended up with the implementation. So in this picture, we have a user to the left, and the user is sort of calling into this CloudState service. And what the user does is that it talks to what we call the CloudState proxy. And the proxy is talking to the user function. So it's almost like Stephan's example with you interact with this instead of the user function itself. So it's sort of, I've toyed with calling it domain injection, because it's essentially taking your domain state and injecting it into your function. And the CloudState proxy intercepts your request and introspects it to see, hey, which service is this for? Am I currently serving this request? And if it's not, then it routes it to the other proxies that exist. So it's a sharding approach. And it has extracted the identifier of the domain object that is targeted for this request. And it then retrieves that state if it's not already cached. And then it passes that state along using gRPC to the user function. So the user function never talks directly to the database. The user function doesn't even have to care that there is a database. It only cares about its domain state and its logic. So this is the clustered setup where you have multiple proxies for the same function. So every single sort of type of function can form a cluster if you have multiple instances of that function. So when you scale out, you can add more and more instances of these, and they will form this cluster together and shard their domain between them and rebalance as needed. And currently we can talk HTTP, gRPC, but we also have eventing support where you can actually essentially subscribe and publish to something like a Google PubSub or similar to have a more non-RPC or non-request response based communication. You can even duplicate so that whenever you get an HTTP request in, I also want the response sent to some event log so that others can observe that this thing happened. So essentially, this is a visual representation of what I described if it was unclear. So essentially it's a ring or a sharded cluster of Akka sidecars, and requests will be routed to the actual sidecar or proxy that is serving this specific entity. So for instance, if you have a request coming in for a customer with ID 1, the proxy looking at that request will see, hey, am I serving customer 1? No, I'm not. I will send it to that other proxy, which is serving customer 1. So that allows very much, there is an I will describe this later because it's a very interesting explanation of what happens when you do it like this. So going into the state models, essentially, this is a simplification of what we have. Essentially, you're just passing the message or the request in, the current state, and you get some message or response out, and you get the new state out. And that's a very high sort of simplification, high level simplification. But for something like event sourcing, what you get is that you get a command in, but you also get an event log, like what has happened before. And you might also get a snapshot of this is the most recent snapshot, and then here are all the events that happened after so that you can replay those and get to the current state. And then as a response, you get the events out that occurred as a result of applying the command. So if the command was place order, then I got order placed events out. So then the runtime can actually store those events and send back the reply. But we also have support for something called conflict-free replicated data types, so that you can actually have multiple function instances modifying the same logical state at the same time. And those changes will then be converged or merged to form a non-destructive merge, so that you can represent something like, for instance, the view counter that I displayed or that I discussed earlier, where you can increment the view counter in many cases, and then you take those increments and you add them together, and now you have the sum total of all the increments. So in this case, you get some state with deltas to apply to that state, and then you can view that, and you can apply your own changes and pass them out. We're also experimenting with adding support for both CRUD, like create, retrieve, update, and delete. And what we're toying with there is we could just pass the snapshot in and get the snapshot out, but you could also think of it as getting the snapshot in and sending some sort of action out, where it's like action is save or action is delete, or what it could be, so that you can represent the domain in the way that makes most sense for your use case. On that topic, we're also experimenting with adding key value support, native key value support, so that you can have a very more dynamic, in an encoding way, you can almost see key value as having CRUD, but where your entity type is a map of keys to values, and you can sort of add or remove them. But knowing that you have a key value representation means that you can make so many more interesting optimizations in the runtime to say that, okay, so this key was removed so that we don't need to save that, or this thing was added and everything that is added can be compressed and done this way. So it's better to have it as an explicit state model. Oh, of course, I mean, there are always use cases where you might want to create something which is stateless currently. It might evolve to have state in the future, but currently it does not. And what's interesting is that since we've chosen to go with gRPC contract first, there are, and with this sort of, all of these things that we've discussed before with having state models being explicit, etc. There are a lot of features that we can sort of offer for free in this proxy or in this thing that you talk to when you try to invoke the service. So there's out-of-the-box support for something called gRPC server reflection, so that when you talk to the proxy, it can present its interface or contract to you programmatically. So you can sort of explore interactively what a service looks like or does. And that means that you can even call it on using command line tools, for instance. We have out-of-the-box support for gRPC web, which means that you can call these services from a web browser, for instance. We have support for something called HTTP API and HTTP body, which is, I think it's a Google Cloud Platform standard or way of encoding how you deal with content types. So if you want to respond to a gRPC request with like a CSS file or a JavaScript snippet or anything that changes the nature of the response type. And the HTTP API is automatic. So when you create a gRPC service descriptor, you get an HTTP API for free. We derive it from the gRPC definition. But you can also customize that if you want to sort of craft your own URIs and your own mapping of which parameters should be extracted from where and put where. So it's very configurable. You can even have multiple of those so that you can expose the same endpoint in multiple URLs, for instance. And of course, as I said before, we can add eventing support without the user needing to know anything about eventing, because we control the invocations and the responses. And of course, there's a ton of different things that we can do. We can keep track of stuff like IO latency to talk to the database. We can keep track of user function latency, for instance. There's a lot of features for free to be had with this type of solution. I'm actually running a bit out of time, I think. So I will probably skip this for now. We can discuss it later. I will also share my slides with everybody. But here are some interesting links if you're curious to know more. And there are also multiple language support in progress. So if you have like your favorite language that you would like to have CloudState support on, then just join the people working on that right now and contribute and provide feedback. Thanks everyone for listening, and I am done.
Yeah, thank you so much, Viktor. And yeah, please, maybe later on we can share a bit of code as well. Like maybe you have, I always love it to share like parts of code. And one advantage of this is that afterwards you can quickly go to GitHub or something like that and just show like nice examples.
Absolutely. There's actually a ton of examples in the GitHub repo. So if you're curious, not now, but after the talk, so you can go and have a look.
Yeah, I see there was a whole discussion about sidecars and what they can do, and that sidecars can be really big as well. I think it's a very interesting concept, and it really, it's a nice separation of concerns in this way, and at the same time, it scales out also very nice without involving the end user, the developer here too much. So yeah, wait, I'm going to my mind map. So we've had our first speakers. I thought it's very interesting to see the different takes also on stateful function as a service. I believe there's more than enough to discuss about. It's also a very new topic, probably also for the speakers and for us. So that makes it extra interesting to really discuss about the pros and cons of different approaches. So with that said, we come to the fourth part of tonight's meetup, panel discussion. Asterios, Stephan, Viktor, please make sure you have the mic on. The idea is just to keep a mic on, so we don't have to bother too much with turning it on and off and stuff like that, and then you forget about unmuting it. So prior to the meetup and during the meetup, we have collected a couple of discussion topics. And one topic that came up in the preparation of this was things about safety guarantees. So like it's one thing to have like a complete cluster of different functions going on and having all their own state. Our question was really like, how does that evolve over time, and how do you make sure that the evolving of a system remains basically safe? And with safe I mean like type safe, so you're not maybe an event changes or something like that, or an event structure changes. Can we achieve these safety guarantees when systems are evolving, or do we need like version schemas? And I want to first ask the question to Stephan. How does Flink and StateFun handle this? Is this essentially different than CloudState?
I guess not so much. So I quickly mentioned this in the when I briefly showed this demo code. So at the moment, all state and all events are also defined in protocol buffers, which is an inherently evolvable format. So I think that's a start definitely to make evolution simpler, both of messages and of events, to start with something that's inherently versioned. There are a few more things you can do in terms of making developing an application forward that go back more to some of the Flink capabilities. So Flink has this notion of distributed snapshots that you can take, or save points that you can take, and that in newer versions you can also manipulate. It's a little tedious still to manipulate them, because you actually need to write like a Flink job to manipulate them, but we're actually in the progress of adding a SQL adapter in order to manipulate them. So you can also, if you wish, so at least in future versions, that's how we envision it, just take a distributed application snapshot, which basically includes, think of it like a database dump, right? It includes the state of all these things, of all the functions. And then run a SQL query to adjust it. You probably need a user-defined function in order to handle the protobuf type or so, but with something like that, you should, I guess, have pretty decent tools available. Inherently version types, and then something like a common query language also to work with your state.
Mm-hmm.
That's the direction we're thinking in.
I think the entire realm of compatibility needs a bit of constraints on it, in terms of what are you trying to guard against, or what are you trying to protect, or make sure that it still works. So for instance, if you need to have both forwards and backwards compatibility, then if the backwards compatibility is layout wise correct, but it might not be semantically correct anymore, then there are multiple sort of levels of compatibility and multiple directions of compatibility. So I think it's worth spending a bit of time looking at what kind of data that you're actually working with for that thing, and see what kinds of guarantees do we want to provide for this specific service. So for instance, if you don't ever anticipate to roll back, you only roll forward, then you might just be able to do repair on read, so that you upgrade whenever you're reading. If you're reading something old, you just sort of upgrade it to the next format so that you can use it. But if you need to go both ways, then you have to essentially decide whether is this, even if it's layout wise correct, am I going to have some other effects on my system from having multiple versions of the service doing different things, even if the state is sort of compatible. So if we think about it, I mean, most software, I think, does not even roll back. It's just you make a change to your schema, you run some upgrade migration script, but most people don't write it in reverse so that they can undo the changes that they made. And if you need to be able to do both for each and every single upgrade, and you need to maintain them forever, like this needs to be backwards compatible with the first version, then that is a lot of applying and unapplying changes if you ever decide that you need to go back 5 versions or 10 versions even. But I think the most important thing is that you have a means of controlling, so that you're in control of your own destiny.
Right. I think what the second part that you described, Victor, I'm not sure if there even is like a theoretically general solution to that, right? I mean, if you go back in your state form and your application logic, and this often also correlates with the data that you process, because chances are good you evolved because your input data evolved and so on. So yeah, So one thing, without wanting to make this sound like, I'm really just pushing for some fling concepts here, is we've actually made some really nice experience with this idea of distributed snapshots for applications, because the one thing that it really gives you is that it aligns basically all these functions together, if you wish, in a point in time. It's not something that comes that comes kind of, I would say, naturally in the way you think about it. If you're used to this, like rolling upgrades, you have to always think, okay, I have to have this forward compatible and so on. But if you can actually come to this point, like think of all these like entities being around, you can trigger a point where basically you let all these messages drain out. So you define a point where all functions have kind of come to a resting point, and you capture them all together, and then you upgrade them all together.
Yep. But that is sort of assuming a closed world assumption. So if you're ever exposed to anything outside of the system, then you're
right. It does assume a bit of a closed world assumption, but when you can actually do this, it's actually a nicely powerful tool. And I don't know, maybe there is so much exactly where this closed world assumption breaks that never actually seen this really applied in the application space. But I think it's definitely something that where the application space could take a cue maybe from the data processing space.
To bring the discussion forward, because I saw an interesting question from Jan-Pieter van der Heuvel about the snapshotting. He asked, how does that work in the case of failures? I guess snapshotting state means that not every message event is immediately persisted. In the event of failures, how do you get the entire system in a valid state again if every function is snapshotting their own state? Right.
Okay, there's a bit of a theoretical answer to it, and then there is actually what Flink does. So in the theoretical world, yes, these snapshots, you can think of them as a specialized way to make some transactional, to complement transactions. You can think of, you're basically picking up a message, mutating the state and writing this out, and you can, if you wish, log all of these things persistently, and then if you wish, a snapshot is basically, it's almost like a group transaction of doing a bunch of these things and not logging everything individually, but logging the resulting effect of this, if you wish, or persisting the resulting effect of this. And you can do this in theory, like each chart or each function individually, or you can actually do this holistically. You can say we're all taking a snapshot together. So in this case, like both in Flink and I think also in CloudState, the important thing is not the function snapshot, but the system that handles the state, like either the Akka cluster or the Flink part does it. So the function itself doesn't actually snapshot. And in the Flink case, it's basically this variant of Chandy Lamport, how you basically capture all of these different charts and state entries and messages together. It's not strictly Chandy Lamport because it tries to eliminate in-flight data as much as possible, and not include it in the snapshot. But yeah, that's basically how you draw a distributed snapshot of multiple entries together. Kind of interesting. This idea has been around since the, I think, 70s or 80s or so. I think it's kind of been reapplied every decade in a different context. It's also one of the timeless things, I think, that are really, in my opinion, great ideas that where history repeats itself.
Read it too, by the way, and wrongly implemented, and then later on found out that there's a theoretical basis for it. I'm not sure about. I know that for example MongoDB had some issues at the start. I was wondering because Asterios, you before the talks you said there might be a need for IDEs that have support to really view what was going on in a cluster of FaaS services, and especially with state introduced, that makes it even more important. Do you have any ideas of how that would look like?
Yeah, so there's a bunch of things. So if everybody keeps input requests persistently, like for example Flink does, or I think Akka does as well with the queues, with the persistent queues, all you have to do basically is, let's say you are in front of your IDE, and you want to debug that function of that specific shard of yesterday between 7 and 8. So all you have to do basically is replay the system up to that point that you want to debug, snapshot the state, bring it in front of your IDE, inject it in your program, do, I don't know, breakpoint step-by-step debugging, and then after you solve your bug, you're done. Now this sounds very easy, but actually you can imagine how much tooling you will need to achieve something like that. Now I don't know how it works in Akka. I was wondering actually, Viktor, could you talk to us a bit about how state looks in Akka? How does it look like? Can I query it from the outside? Can I download it in some way?
Yeah, so how it's currently working is that it sort of depends on the state model. So for instance, event sourcing is represented as an event log, and we're actually working on something that we call projection support, where you can actually consume this event log and produce something like a database view or do some aggregation on it in a more sort of eventually consistent way, where you can have multiple processors keeping up and producing their own view of the world. So I think we're going with the approach where every domain or every service, if you want to call it that, is in control over its internal representation, because otherwise it's very easy that things leak out, and then you can't really easily change things internally, because it's so you have sort of implicit contracts with others on how your state should look. But you could think of, if you represent your state as CRUD, for instance, and that CRUD data is stored in a SQL database as a table representation, for instance, then you could have a different way of projecting that information to other systems. But I think the main philosophical difference between the approaches that we're taking here is we have a more sort of open world assumption where every single service could be like, you're talking to it as if it's a gRPC based service, could be anything. Mm-hmm. And you could have multiple different things implemented in different ways, and you wouldn't know what's actually implemented underneath, or how it's implemented underneath. And since every single service is forming a cluster with its own instances, so for instance, you could have 1,000 cluster of just one single service that is scalable independently of all other services. And I think that the real challenges in distributed system is knowing where to draw your boundaries, how to specify your contracts, or going back to what we said before with availability versus consistency, setting these boundaries, annotating, this is an eventual boundary, this is a consistent boundary, or this is so that you can reason about which assumptions can I make within this boundary, and how can I sort of use that knowledge of my external contract so that I can create something better based on those constraints. So like my closed world is inside this boundary, and I can have multiple of those side by side depending on what the actual use case is.
Stephan, what's your reply to that?
Yeah, I think that's actually well put. So these especially this, you have to know where your boundaries are. So so just looking at this, at this trade-off, consistency, eventual consistency with availability and so on. I think it makes a lot of sense to exactly think very hard about what's a meaningful boundary here, because I think in the microservice space there was a tendency to overdo things. Like you have decoupled things into 3 different services, but none of these services actually functions without the others. So if one is down, the others really can't do anything, right? They strictly rely on each other. This I think the example that Asterios gave is actually one of these examples. And if you have such an example, you might as well model them. You don't have to overdo it with breaking the circuit, placing the circuit breakers and doing the eventual consistency and so on. Just like if these actually are available or unavailable together, then it can make sense to treat these as a tighter unit. And then of course these compose into the larger infrastructure with other units where you definitely do want eventually consistency between them, and and emphasis more the availability side, like have them much more loosely coupled. So I think this is going to be a very interesting question, how this looks like in the long run. So I think in the end a lot of companies do try and go for something like that, that they have small units favoring consistency composed with eventual consistency, where the like the composition layer is often something where not the individual teams have to worry about it, but the teams then work within one boundary where they can assume a bit more consistency. That can make things easier. So I think this is going to be very, very interesting. So I like the thing about StateFun that Viktor says that he wants to keep that open and model this as as annotations and see, okay, we do need stronger consistency here, looser consistency here and there, right, on the CloudState side. I think on the StateFun side, we've kind of opted a little bit for the let's say consistency first, to say like this makes sense in one unit where you say, okay, these anyways they go together. There's no way that this function can in the end really do anything meaningful if the other function isn't there. So if the other part becomes unavailable, it's okay for this other function to also, like back pressure and process its events a little later once the other function has come up again. And so it's more suitable, I think, for these, let's say, smaller units. And if you want to, for example, compose it then into bigger, more loosely coupled units, you'd probably, have different units of StateFun applications coupled by ingress egress pairs like messaging through Kafka or so between them, and thus have them slightly less coupled. But arguably even Kafka is not a system that goes for total availability in favor of reduced consistency, because there's also an availability limit there with if you have partitions, minority partitions become unavailable and so on. So yeah, I think I don't know what the perfect answer for the large picture composition is, but I think in the small picture it's always been my take, making it easy by keeping tight units consistently together can actually be quite helpful.
I personally am most interested as well in like, do we need some kind of design principles for microservices and also FaaS systems? Because what you just said is something that I think rings true to many people, is the kind of domain modeling that you do determines very often the kind of structure. And that structure is not always amenable for a certain design, if you know what I mean. Mm-hmm. So do we need to kind of, before talking about all the technology, first talk about the kind of principles that is needed to design this?
Yeah. And maybe one thing to add, I think the thing that where microservices that comes into play there's often, I think, two aspects. There's not only the modeling this as independent units that can fail over and be available in independent manner. It's often also just the team organization, like the different teams work on different microservices. But if you have 3 teams working on 3 different things, it makes sense to think of them as 3 different services. But if they really require each other strictly to function, then they don't have to be different failover units strictly, because then you're trying to do a lot of work in loosely coupling, and you don't have to. You're just making your life hard.
Yeah, but there's also the case where you have these sort of convenience dependencies. Like, for instance, if you want to serve something quickly, you might have a loose dependency on a cache, for instance. Instead of computing it yourself, you might have a loose dependency on a cache and say, hey, if I've already computed it, let's send it out. And typically, that thing which is cached is kept somewhere physically else. I mean, it's not in the same point in space-time as the rest. So even if it's on memory or if it's on disk, you're going to have to communicate with some other parts of the system in order to retrieve it. So I don't know if I might go overboard, but I essentially view everything as a potential service. But like even the consumer is a part of my system, because ultimately if the consumer fails to send their request, can they retry their request, or should they not retry their request? Or like, if I try to retrieve my thing from the cache, do I have to care whether it's local or if it's remote or if it's served by some other, it might be served by some device or something like that. I think ultimately it's about failure boundaries. So if those things either fail, then they can have a type of coupling, because as you say, I mean, if they cannot survive without each other, then it doesn't matter if they fail together as well, because they can't exist without each other anyway. But on the other hand, I think there are many cases where you can have like a fallback approach, like, okay, I couldn't get the thing from the cache, so I might be able to retrieve or compute it myself, or I might not be able to get the value that the user wants, but I can send back an approximation or the last known value or something like that. And I think it's yeah, focusing on sort of the progressive or like degradation, like if this thing doesn't work, is there anything that I can do that would have any value?
Yeah, that's very interesting. I think that's also interesting because in a good design, you really look at the edges of the system, and the edges are often the most interesting to design. I have a question from Michael Hempel, and we have limited time. I really believe like we could make each section of this 1 hour, and we would have a lot of fun as well. But when it comes to orchestration and choreography in stateful function, is this something that you are working on, or have any idea of what your take? What are your ideas there? And then the second question probably is, and what's your take regarding WebAssembly? But let's first focus on the orchestration and choreography part. Anyone wants to chime
in?
Go ahead.
So, okay. So, I think in some sense I would say do what feels natural to you. The idea is that this doesn't require a specific way of orchestrating or choreographing it, if I said this correctly. So the example that I gave in the presentation is that you know, the function logic fits very well on something like a stateless Kubernetes deploying, you know, with an autoscaler, or on an FaaS framework or so. And then Flink itself fits also well on, you know, on some other deployment. The scaling is a little more tricky there. I mean, you can scale it, but you can't scale it that rapidly because it involves moving state around, and just moving state takes time. So yeah, you would probably deploy this with something like a Flink Kubernetes operator or so, if you want to run it on Kubernetes, and use that to scale it up and down. But you know, you can also just deploy it somewhere on bare metal if that's what your tooling does, and you know, bring up machines and configure them with Chef, and put the functions behind whatever whatever intermediate service layer so that you have. So it's really supposed to be not prescriptive in how you do it. It's meant to fit naturally with what, you know, what's coming up as common ways of doing it with, you know, with cloud infrastructures and Kubernetes, but it's not strictly requiring this.
Mm-hmm. You have a bit more. You have more approach where you seem to want to model the whole system from the outside. Is that correct?
What do you mean, model the whole system? So it's, oh yeah, I mean, it's a bit of a full stack, if that's what you mean, right? The whole thing basically is a combination of, you know, Flink as you know, instead of a database or so, and then functions as their separate deployment. So you don't need to attach this to another like existing database or something like that. I'm not, if that's
No,
what
sorry,
you're.
I was actually asking the question to Asterios.
Okay.
Yeah. Sorry. Also to get a bit more different takes on the question with choreography.
So on the question of choreography, so basically it is with microservices, for example, if you have a choreography, you may get, let's say every microservice endpoint is a function. If you have a choreography, it means that there are functions within functions that call functions, right? And then this is choreography. Naturally, if you look at functional programs, we do choreography. Let's say the main function would be the orchestrator, but after that, there is a lot of choreographies of functions basically calling other functions, etc., etc. So if we release the developers from the past, I think they will tend to do a lot of choreography in the end, simply because we will not have to force them to deal with the peculiarities of the technology they are using. So if we give pure functions that call pure functions to users, it doesn't matter anymore. It's not a question anymore.
So I have a different interpretation of the question, and I don't know if it's right or wrong, but I will actually answer it anyway. And I saw it as orchestration of slightly more to your Asterios, your interpretation of essentially orchestrating the interactions between different services. And my opinion there, or my current understanding, is more along the lines of doing something like the Saga pattern or process manager, where you can essentially say that this is what I want done, and this is what I want to undo, or this is how I undo it if I can't do it. But I think that specific pattern needs to be evolved a bit more to support things like, is this an idempotent operation? Can I retry it? How much can I retry it? Is there a quota associated with it? Especially now, I think now more than ever in the history of the world, every single thing becomes more and more interconnected. You have systems that depend on other systems for their functionality, other web services, other backend systems, business to business functions, etc. And having or spreading that information into the client itself. Like, what are the constraints of the backend? How do I deal with the constraints of the backend? And having a richer way of expressing that in the contract itself, so that, because to be honest, whenever I see a timeout encoded anywhere, it's almost always 1 second, 3 seconds, or 10 seconds for some reason. That can never be a correct value. I mean, we need to be able to derive more information about expectation. Like, what is the distribution of the response times for this function? How do I want to place myself? How long do I want to wait? How many sort of standard deviations do I want to be off in order to consider this alive? I think there are many more dynamic system properties that we haven't really been able to bring into the programming aspect of things. And it would be nice if we could do that for the programmer in a much more sort of tangible way than having to specify everything manually.
Should it be like part of a type system or something like that? I spoke with Eric Meyer about that once.
I think the problem is always that when you write the program, as the programmer, you might not even know where it's going to be deployed. You might not know how the services that you're depending on, how they're going to evolve in the future, or how much their behavior is going to change over time. So ideally, we would have some sort of adaptive system that learns from its interactions with it in the past and sort of figures out, okay, this is what we want to deliver, but this is what this can deliver right now, and how do we map these two things together so that we don't overload each other and we don't bring each other down.
Yeah, it's a little bit what I also I think that the idea comes from Akka Streams with its back pressure IDs and stuff like that. So right, very beautiful answer. I wish we seriously, I really do. I wish we had like an hour more, and I think there are like many questions, also new questions come in. But we set the time limit at 20 minutes. I'm pretty sure we're past it right now. So let me just go back to my notes. I like notes, sorry. So first of all, thank you. Really, I thought it was a wonderful discussion. I also hope that there will be more discussion at the breakout groups afterwards. If it's all voluntary, if you feel like you want to break a beer. No, not break it, open a beer, then please go ahead. Like I said, unfortunately, normally I would have invited you all to join us for a drink in the foyer. There is no foyer, there's a foyer here, but I mean, I bet you can't come here. So lacking foyer, and we do have drinks here, but yeah, that's the same problem. So we still understand really the social aspect of a meetup. I always thought it was really important to meet new people and to talk about technical topics in depth. So we'll keep this meeting open for general discussion. We've made 3 extra breakout Zoom meetings, if I'm correct, for individual questions to the speaker, to further discussion, a little bit like sometimes the speaker stands a little bit like on one side, and then, there might be some questions and stuff like that. We're trying to recreate it a little bit here in this virtual environment. So please take a drink of your choosing from the fridge, if that helps set the mood a little bit. With that said, we really hope that this will bring back a little bit of the original intent of a meetup. Thank you again so much for attending, and we hope to see you virtual or in real life at the next data engineering meetup. I would also like to thank again Asterios Katsifodimos.
Don't.
Sorry.
Yeah.
Stephan Ewen, Viktor Klang for being with us, albeit all virtual at the meetup. Thank you all for joining as well, and for all the questions that are asked. And of course, I would particularly like to thank Ruud-Jan Poel, Aniko Hoekman, and Juris Bukela, and of course my employer, Big Data Republic, for making this all happen. Thank you very much.
Thanks a lot for inviting us also. That's really cool, and especially because you had to organize it twice, so double the work. So it's cool that we actually made this happen after all.
Thank you as well. Yeah.
I 100% agree.
Sorry, what?
Yeah, I totally agree.
Yeah, okay. Yeah, and I hope, you never know with this whole situation that maybe the next meetup we can do in real life, maybe outside. I've also heard about meetups that have been held outside with 1.5 meter distance and stuff like that.
Or in cars.
Sorry?
Inside cars. People meet in cars lately.
Oh, really?
Yeah.
Okay.
Like drive in a movie theater or style?
Just drive in a concert, for example. There's a concert and you just park your car in a parking, and then that's you honk instead of clapping your hands. And
All right.
I'm reading Jan-Pieter van de Veulen's Inside Sidecars.
not inside cars, yes.
Yeah. By the way, please right now you can disable the mute if you like. I hope it will not be one big extreme, like everyone speaking at the same time, but right now we are basically in a virtual place where everyone can speak freely, so to say. So yeah, let me see if we have anything else right now. But I think very, very interesting is should code deployment itself not be like a function, so you basically have this whole functional programming approach where the behavior itself is a transformation over the system that you already have.
You just need to pass in all your users into it.
Yeah, well, you have the outside factor, of course. Yeah, that's going to be a problem. I agree. And
I mean, you can do certain things like that. I would bet with actually Akka or stateful functions right now, right? Because all these things can actually spawn other actors, and you can actually build these things to be interpreters of other stuff. So I think you can actually build a system where functions actually deploy other code or sub workflows. That I don't really see a reason why that wouldn't work. Not sure it fits super well with this paradigm also of immutable deployments and configurations, which I don't know, it's also pretty valuable. But if somebody wants to do something like that, probably should work. I mean, what do you think, Viktor?
Yeah, I mean, it depends on what you want to be able to allow. So, for instance, do you want to be able to allow durable or recoverable state? Do you want to allow? How do you do coordination, for instance? How do you do coordination if things deployed on multiple machines? Like, you need to share knowledge about what exists where and when, so that you have 5 machines, and they're all different functions. How do they know about each other so that they can? You need to draw your boundaries somewhere where the sort of functional application of the world sort of stops, and now we're interpreting it. And
right, so you would have to have some I don't know, derived deterministic naming addressing schema so that you use in order to just discover each other also.
The only thing that I've seen works is when you have a single interpreter, so that you can actually say that, okay, this function should, when interpreted, deploy on these machines over there, so that you have all the knowledge that you need so you can drive the workflow with the interpreter. But then you can't deploy things separately, because now how do I know about that thing? When do I know, like time-wise, how does information propagate such that this thing now knows about that thing? So yeah, I think my approach is actually going in the opposite direction, like gaining some sort of inner peace with effects. Like,
yeah.
The world is effectful, and somehow we manage to live in it anyway. So how can we have like coping strategies for effects? Because ultimately my philosophy is that programs are just encodings of solutions. So the solution can exist outside of the encoding. Like, just as before we had computers, we had order processing. It's just that we did it humans with pen and paper or whatever it was. So programs are only encodings of solutions. And since we can solve things in different ways, we can even solve it without programming. The question is, how does the program solution interact with things that are not program solutions?
Mm-hmm. Yeah.
But that's very sort of abstract and high level. It's
No, but I think it's essential actually, in my view, because our whole view of computing has changed in the last decades, 2 decades perhaps, and we went all the way to from single core execution and total knowledge, closed systems basically, to open-ended, more Carl Hewitt 1970 style thinking, and it makes sense to also rethink basically the boundary within which we want to do computing.
Mm-hmm.
Yeah.
But I think this is actually a great analogy for this whole thing also, because still with this whole multi-core distributed systems, there's still a lot of stuff that you write single-threaded, and you want this as one unit, because in that model it's just super simple to reason about it. And then you go multi-core when you actually do need it. Mm-hmm. Or the part that that you connect across multiple cores via something like messaging, there within one one function, invocation, one actor, you have this very nice assumption. And then you compose maybe that to even to even more distributed clusters and entities that you can just treat this as different cores running somewhere else, and you talk with messaging. But if you want, you can also take the different latencies and communication guarantees into account, or you can take into account that the ones that run on multiple cores onto the same machine fail together and live together. But I guess the point I'm making is when you are still on a single thread, you really want to exploit that consistency that you get. And I think that we should also keep doing when we build our distributed applications. Like within a small unit, we do want to go for something simple.
The weird thing is that
basically compose it as we go out.
But the weird thing is that then the processor actually tries to speculatively execute things in parallel anyway, as long as it can hide any effects from you. So
exactly, but it never shows that to you, right? And it does it less though than it used to do for all the security reasons. But
yeah, but I think it's interesting that we're still on a computing architecture or an interpreter architecture that doesn't support message passing. Like you can do reads and writes, but you can't send messages. And you have this cache coherency protocol on top of it to make sure that, hey, your simple reads and writes, that is the communication protocol, but there is no knowledge about the actual data. So I think it's some sort of multiple levels of CISC versus RISC, where every single layer that throws away information needs to be almost statistically or speculatively regained at another level. So it's like, yeah, I only know that this is a move instruction because everything else was thrown away, because this is the fastest, most compact representation of what we were trying to do. But we have removed all the context around why we're doing it. So the thing that's supposed to evaluate that can't really do much, but just that. It doesn't know that it's not needed anymore. So then to figure out that the move is an unnecessary instruction, it needs to do look ahead to see, okay, you want to do move here, but so in the future, you're actually not using it until you sort of, okay, so I don't have to do it. So we're sort of in multiple steps, sort of aggregating information, throwing it away, trying to recreate it later, throwing it away, trying to recreate it later, throwing it away. And I think it might be one of these sort of inherent problems in the world where it's, you can't afford to keep all the context all throughout the pipeline because ultimately it's too expensive. And if you're only like a RISC machine or something like that, so you program only with reads and writes basically, then it's too cumbersome. We need something more contextual, more that has more meaning.
Mm-hmm. Yeah, I don't know if I agree with this. I think actually that the folks that built these processes have done a very admirable job to allow something where you can actually build something like message passing really efficiently. You know, one core writing to a cache line, if it's not referencing it anymore, but it's referenced by another core, it moves over there. If it's, you know, if the, let's say the target of the message is on the same core, then it will stay there for locality. So you can actually do, if you pay attention to the way that the hardware works, actually do very efficient message passing on top of it, and then still then also the coherency protocols don't get much in your way if you don't have too much, you know, false sharing and so on. But at the same time, for those folks that do not want to use that abstraction, but rather say, you know, we do want shared context, and yes, we pay the price that the shared context has to be, you know, re-derived from other, you know, more expensive hierarchies further, memory hierarchies further down. When necessary, then it actually works. It just comes at a price. So I always thought that from everything I've seen in distributed systems, like the cleverness of what the multiprocessor hardware architects do, I'm always in awe when I see this, because they have kind of struck this trade-off well. I think you can do the message-based system, but they also have a really cool way to give you a much more consistent view, you know, within boundaries, if you actually want to use that for simplicity.
Well, the interesting part there is that the cache coherency protocol tends to be a message passing construct. It's almost like a two-phased commit, but for cache. Yeah. But whenever we write to a cache line, that's one thing. But how do we receive messages? It's like, okay, now there's really no primitive for receiving messages except for like hot spinning on top of a cache line to figure out whether it's changed. Or it would be interesting. Like, what would the world look like if there was a primitive for sending messages at the hardware level, to get more sort of asynchronous, especially with these sort of 64 core CPUs, etc. It's going to be tricky or costly to do cache coherency across 64 cores. And
yeah, I do know of certain
depending on how much you share, yeah, how much cache line sharing you do.
Yeah, if you don't share, you don't need coherency either.
Right, that's what I meant. If you build the applications in such a way, then you're almost at a message passing level. You never share it between the two. One produces it. If somebody else consumes it later, it's perfect. And it just flows like a message. You're right. The notification that this happened is cumbersome. You do need maybe spinning. Maybe I don't know what, to be honest. But if you don't want to think in terms of that, if you want actually some assistance mechanism that, you know, gives you the consistency, then you actually have it, and that I find pretty fascinating. So you can use it both ways almost.
Yeah, but that's the fascinating aspect, that we can actually layer everything on top of each other. We can have a CISC layer that precedes a RISC layer, that precedes a CISC layer, that precedes a RISC layer. And it's all translation with information either being discarded or trying to be inferred. So it's the same with message passing versus just read-write memory address.
Yeah, and I think in this description from Asterios, there is something quite interesting in there. This, I think, Cloudburst project from Berkeley or so. And in some sense, I think that's kind of the direction that's happening there, right? I think they're trying to do the stateful serverless in almost that way. You have this proxy, this caching layer with something like a Snoopy bus protocol or so, but between different machines, and try to do actually cache coherency between different processes. And when it works, it's actually quite fascinating, because then you can work in your distributed systems almost as if you were on a single machine. And, you know, with the performance trade-offs, exactly like you said, cache coherency, if you share lots, is expensive, but you can pretend that you have this cross machine consistency. It's fascinating research. I'm just wondering if, you know, again, like you said, if you adopt message passing in the first place, you just simplify the problem so much, and then you can get rid of all this expensive layer. And so in some sense, if I look at these projects, like I think StateFun, CloudState, they just say, okay, so it's all pure message passing, and then we don't need all this currency stuff. And I think the Cloudburst is exactly more like, okay, we're trying to do the same thing that the hardware does in currency in a distributed system, with all the pros and cons of that.
That's really interesting, because that would also scale nicely to smaller architectures that are more embedded. So you make it basically agnostic on the kind of underlying processor architecture, if I'm correct.
Maybe honestly, I have to look a little more into this if this would allow it. I only know like the very high level summary from this approach.
I do know of certain CPU architectures that are really designed for routing and message passing on the chip, and that also have an operating system that is suitable for it, because the operating system layer is often a problem then if you want to you need to basically distribute your operating system over the CPU die basically in order for it to work effectively, and to distribute the state and distribute also the knowledge of the state on the die itself. I think it was called barrel OS, if I'm not mistaken. Barrel OS.
Just a quick question: What do we do with the breakout rooms now? Because do people actually go to the breakout rooms at the moment, or?
I'm not entirely sure, to be honest. I
don't think anybody went there.
No. Yeah, well,
because we are still here.
It was indeed, it was worth a try. And I also appreciate the discussion. So the only thing for people still listening, I mean, please unmute if you feel like chiming in. And I just saw from Ruben Simons that he knows of a processor architecture that looks a little bit like that. The Intel IAPX433. I've not heard about that, by the way.
Me neither.
Yeah, Peter Hofstee work in Cell. Yeah, Cell, that was it. Yeah. Yeah, these are very interesting topics. I'm also not an expert on it, but really to take the whole message passing idea on the silicon level.
Hi guys, can you hear me?
Yeah.
Yes.
Oh wow, my microphone is working. It's a miracle. Yeah, I was super interested. I really wanted to thank everyone for the talk, because this is very insightful. And when you guys went a little bit to the lower level, I was also very excited, because I've always been a little bit interested in non-standard computing architecture. So the two links that I put into the chat for the IAPX432 and the cell microarchitecture, and then especially Peter Hofstee's work in the cell is pretty interesting from a perspective of how hardware could be done a little bit differently from how we do it today, essentially. So I thought it would be interesting to share that with you guys.
Absolutely.
Yeah. Thanks a lot for pointing this out. Yeah.
I now have I hear a little bit of an echo. Is that correct?
Not anymore.
Okay. And when it comes to I'm looking at I was looking at open source software development of the cell microprocessor architecture. Do you feel like, does anyone feel like sharing some code and showing some ideas there, maybe something that we are particularly proud of?
I can actually show just a couple of files, very small files, because I'm running into a bit of a deadline at 1:30. So if you don't mind, I would definitely want to give people a bit of a demonstration.
Yeah.
Cool. Let's see here. So I guess everyone can see this. So this is essentially the only thing that is necessary in terms of CloudState enabling a gRPC definition. And what we use is something called gRPC annotations, or protobuf annotations. And the only thing that you need to specify is what parts of my parameters identify the entity or the domain object that is sort of involved in this request. Mm-hmm. And this is a sort of very sort of low overhead in terms of doing things differently in gRPC. And I can also show you, we have a more sort of shopping cart example where I can show these HTTP annotations. It's the same thing, it's from GCP, where you can create this, so like this will be a post request to this sub URL. It will extract the user ID from this part of the path, and then it will map everything else from the body itself. And that means that when you expose this endpoint, you also get this HTTP endpoint for free. And here is an example of how we plug this into if you want to do eventing. So essentially you can say, this endpoint also listens to the items topic in the eventing subsystem to drive its invocations. And you can also have an out topic there as well if you want to say that it produces its output to this other topic. So this allows you to keep the entire contract and interface in one single file that is separate from the implementation itself. So the implementation doesn't need to concern itself with specifics with regards to where it should get requests from or how they materialize. It's all up to the proxy itself. So the proxy will actually receive this gRPC specification and serve that to the outside world and say that, hey, this is who I am, and this is which endpoints that I support. And it will hook up everything in the eventing to match the endpoints, etc. And as for the code itself, we could, let's say the shopping cart entity, in this case, it's using the event source support. So this is the annotation-based API for Java. And essentially just annotating, this is the method that returns the snapshot. This is the method that deals with snapshots, and then adding an event handler for the different domain events that happen with this entity. So you have item added events and item removed events. And then for the actual endpoints, you add command handlers. So like you have the get cart and add item and remove item, etc. So this code itself doesn't necessarily need to involve itself with any type of IO or data lookup or talking to a specific server somewhere. It's really, I would say, I think the closest thing that I've sort of arrived at is domain injection. It really injects, it's not dependency injection as in injects anything, but it really sort of only injects your domain into this thing. And you only worry about what your domain actually does. And of course, we also have it in JavaScript if you're curious about what the difference would look like. And since this is all just JavaScript code or Java code, you can add and sort of build your own API on top of this if you want to expose it as some sort of that. This is how we do it in our company, or this is my favorite JavaScript framework. I want to have something that looks and feels exactly like that. So it's sort of like an open world assumption in terms of how you could implement your own services. And between the proxy itself and this user function is what we call a language support library that implements the protocol so that they can communicate and send over the state and invocations and stuff like that. So this is quick demo. So I have three minutes. So I can actually answer the question that was sent in just right now. So what we do is we actually separate the public definition and the domain definition completely. So you can define your, you don't even need to use proto for your domain if you don't want to, because ultimately CloudState only cares about bytes and understanding what kinds of bytes it is. So in theory, you could store any kind of encoding of anything you want. We just picked protobuf because we think it's a good standard for dealing with state. And it's also easy to convert it to stuff like JSON or other representation if you want to view it, because it's not super pleasant to look at in raw binary form. Cool. No other questions? There's 1 minute. Okay, cool. Well, yeah, I have to say thank you to everybody. It's been amazing. We could probably sit here and discuss the rest of the evening for sure. I have zero doubt in my mind. It's always nice to see you, Stephan, and it's great to meet you all.
Yeah, likewise.
Likewise, Viktor.